In this video, I'm going to describe various kinds of architectures for neural networks. What I mean by an architecture is the way in which the neurons are connected together. By far the commonest type of architecture in practical applications is a feed-forward neural network, where the information comes in at the input units and flows in one direction through hidden layers until it reaches the output units. A much more interesting kind of architecture is a recurrent neural network, in which information can flow round in cycles. These networks can remember information for a long time, they can exhibit all sorts of interesting oscillations, but they're much more difficult to train, in part because they are so much more complicated in what they can do. Recently, however, people have made a lot of progress in training recurrent neural networks, and they can now do some fairly impressive things. The last kind of architecture I'll describe is a symmetrically connected network, one in which the weights are the same in both directions between two units. The commonest type of neural network in practical applications is a feed-forward neural network. This has some input units in the first layer at the bottom, some output units in the last layer at the top, and one or more layers of hidden units. If there's more than one layer of hidden units, we call them deep neural networks. These networks compute a series of transformations between their input and their output. So at each layer you get a new representation of the input, in which things that were similar in the previous layer may have become less similar, or things that were dissimilar in the previous layer may have become more similar. So in speech recognition, for example, we'd like the same thing said by different speakers to become more similar, and different things said by the same speaker to become less similar as we go up through the layers of the network. In order to achieve this, we need the activities of the neurons in each layer to be a nonlinear function of the activities in the layer below. Recurrent neural networks are much more powerful than feed-forward neural networks. They have directed cycles in their connection graph. What this means is that if you start at a node or a neuron and you follow the arrows, you can sometimes get back to the neuron you started at. They can have very complicated dynamics, and this can make them very difficult to train. There's a lot of interest at present in finding efficient ways of training recurrent nets because they are so powerful if we can train them. They're also more biologically realistic. Recurrent neural networks with multiple hidden layers are really just a special case of a general recurrent neural network that has some of its hidden-to-hidden connections missing. Recurrent neural networks are a very natural way to model sequential data. So what we do is we have connections between hidden units, and the hidden units act like a network that's very deep in time. So at each time step, the states of the hidden units determines the states of the hidden units at the next time step. One way in which they differ from feed-forward nets is that we use the same weights at every time step. So if you look at those red arrows, where the hidden units are determining the next state of the hidden units, the weight matrix depicted by each red arrow is the same at each time step. They also get inputs at every time step and often give outputs at every time step, and those all use the same weight matrices too. Recurrent nets have the ability to remember information in their hidden state for a long time. Unfortunately, it's quite hard to train them to use that ability. However, recent algorithms have been able to do that. So just to show you what recurrent neural nets can now do, I'm going to show you a net designed by Ilya Sutskever. It's a special kind of recurrent neural net, slightly different from the kind in the diagram on the previous slide. And it's used to predict the next character in a sequence. So Ilya trained it on lots and lots of strings from English Wikipedia. It's seeing English characters and trying to predict the next English character. He actually used 86 different characters to allow for punctuation and digits and capital letters and so on. After he'd trained it, one way of seeing how well it can do is to see whether it assigns high probability to the next character that actually occurs. Another way of seeing what it can do is to get it to generate text. So what you do is you give it a string of characters and get it to predict probabilities for the next character. Then you pick the next character from that probability distribution. It's no use picking the most likely character. If you do that, after a while it starts saying the United States of the United States of the United States of the United States. That tells you something about Wikipedia. But if you pick from the probability distribution, so if it says there's a 1 in 100 chance it was a Z, you pick a Z 1 time in 100, then you see much more about what it's learned. The next slide shows an example of the text that it generates. And it's interesting to notice how much is learned just by reading Wikipedia and trying to predict the next character. So remember, this text was generated one character at a time. Notice that it makes reasonably sensible sentences, and they're composed almost entirely of real English words. Occasionally it makes a non-word, but they're typically sensible words. And notice that within a sentence it has some thematic sense. So the phrase "several Irish intelligence agencies in the Mediterranean region" has problems, but it's almost good English. Notice also the thing it says at the end, such that it is the blurring of appearing on any well-paid type of box printer. There's a certain sort of thematic thing there about appearance and printing, and the syntax is pretty good. And remember, that's one character at a time. Quite different from recurrent nets are symmetrically connected networks. In these, the connections between units have the same weight in both directions. John Hopfield and others realized that symmetric networks are much easier to analyze than recurrent networks. This is mainly because they're more restricted in what they can do, and that's because they obey an energy function. So they can't, for example, model cycles. You can't get back to where you started in one of these symmetric networks. In this video, I'm going to talk about perceptrons. These were investigated in the early 1960s, and initially they looked very promising as learning devices, but then they fell into disfavour because Minsky and Papert showed they were rather restricted in what they could learn to do. In statistical pattern recognition, there's a standard way to recognise patterns. We first take the raw input and we convert it into a set or vector of feature activations. We do this using handwritten programs which are based on common sense. So that part of the system does not learn. We look at the problem, we decide what the good features should be, we try out some features, we see if they work. If they don't work, we try some more features. And eventually we get a set of features that allow us to solve the problem by using a subsequent learning stage. What we learn is how to weight each of the feature activations in order to get a single scalar quantity. So the weights on the features represent how much evidence the feature gives you in favour or against the hypothesis that the current input is an example of the kind of pattern you want to recognise. And when we add up all the weighted features, we get a sort of total evidence in favour of the hypothesis that this is the kind of pattern we want to recognise. And if that evidence is above some threshold, we decide that the input vector is a positive example of the class of patterns we're trying to recognise. A perceptron is a particular example of a statistical pattern recognition system. So there are actually many different kinds of perceptron, but the standard kind, which Rosenblatt called an alpha perceptron, consists of some inputs which are then converted into feature activities. They might be converted by things that look a bit like neurons, but that stage of the system does not learn. Once you've got the activities of the features, you then learn some weights so that you can take the feature activities times the weights, and you decide whether or not it's an example of the class you're interested in by seeing whether that sum of feature activities times learned weights is greater than a threshold. Perceptrons have an interesting history. They were popularized in the early 1960s by Frank Rosenblatt. He wrote a great big book called Principles of Neurodynamics, in which he described many different kinds of perceptrons. And that book was full of ideas. The most important thing in the book was a very powerful learning algorithm, or something that appeared to be a very powerful learning algorithm. A lot of grand claims were made for what perceptrons could do using this learning algorithm. For example, people claimed they could tell the difference between pictures of tanks and pictures of trucks, even if the tanks and trucks were sort of partially obscured in a forest. Now, some of those claims turned out to be false. In the case of the tanks and the trucks, it turned out the pictures of the tanks were taken on a sunny day, and the pictures of the trucks were taken on a cloudy day, and all the perceptron was doing was measuring the total intensity of all the pixels. That's something that we humans are fairly insensitive to. We notice the things in the picture, but a perceptron can easily learn to add up the total intensity. That's the kind of thing that gives an algorithm a bad name. In 1969, Minsky and Papert published a book called Perceptrons that analysed what perceptrons could do and showed their limitations. Many people thought those limitations applied to all neural network models, and the general feeling within artificial intelligence was that Minsky and Papert had shown that neural network models were nonsense, or that they couldn't learn difficult things. Minsky and Papert themselves knew they hadn't shown that. They'd just shown that perceptrons of the kind for which the powerful learning algorithm applied could not do a lot of things, or rather they couldn't do them by learning. They could do them if you sort of hand-wired the answer in the inputs, but not by learning. But that result got wildly overgeneralized, and when I started working on neural network models in the 1970s, people in artificial intelligence kept telling me that Minsky and Papert had proved that these models were no good. Actually, the perceptron convergence procedure, which we'll see in a minute, is still widely used today for tasks that have very big feature vectors. So Google, for example, uses it to predict things from very big vectors of features. So the decision unit in a perceptron is a binary threshold neuron. We've seen those before, and just to refresh you on those, they compute a weighted sum of the inputs they get from other neurons. They add on a bias to get their total input, and then they give an output of 1 if that sum exceeds 0, and they give an output of 0 otherwise. We don't want to have a separate learning rule for learning biases, and it turns out we can treat biases just like weights if we take every input vector and we stick a 1 on the front of it, and we treat the bias as like the weight on that first feature that always has a value of 1. So the bias is just the negative of the threshold, and using this trick we don't need a separate learning rule for the bias. It's exactly equivalent to learning a weight on this extra input line. So here's the very powerful learning procedure for perceptrons, and it's a learning procedure that's guaranteed to work, which is a nice property to have. Of course, you have to look at the small print later about why that guarantee isn't quite as good as you think it is. So we first had this extra component with a value of 1 to every input vector. Now we can forget about the biases. And then we keep picking training cases using any policy we like, as long as we ensure that every training case gets picked without waiting too long. I'm not going to define precisely what I mean by that. If you're a mathematician, you can think about what might be a good definition. Now, having picked a training case, you look to see if the output's correct. If it is correct, you don't change the weights. If the output unit outputs a 0 when it should have output a 1, in other words, it said it's not an instance of the pattern we're trying to recognize, when it really is, then all we do is we add the input vector to the weight vector of the perceptron. Conversely, If the output unit outputs a 1 when it should have output a 0, we subtract the input vector from the weight vector of the perceptron. And what's surprising is that that simple learning procedure is guaranteed to find you a set of weights that will get the right answer for every training case. The proviso is that it can only do it if there is such a set of weights. And for many interesting problems, there is no such set of weights. Whether or not a set of weights exists depends very much on what features you use. So it turns out that for many problems, the difficult bit is deciding what features to use. If you're using the appropriate features, learning may then become easy. If you're not using the right features, learning becomes impossible, and all the work is in deciding the features. In this video, we're going to get a geometrical understanding of what happens when a perceptron learns. To do this, we have to think in terms of a weight space. It's a high-dimensional space in which each point corresponds to a particular setting for all the weights. In this space, we can represent the training cases as planes, and learning consists of trying to get the weight vector on the right side of all the training planes. For non-mathematicians, this may be tougher than previous material. You may have to spend quite a long time studying the next two parts. In particular, if you're not used to thinking about hyperplanes in high-dimensional spaces, you're going to have to learn that. To deal with hyperplanes in a 14-dimensional space, for example, what you do is you visualize a 3-dimensional space and you say 14 to yourself very loudly. Everybody does it. But remember that when you go from a 13-dimensional space to a 14-dimensional space, you're creating as much extra complexity as when you go from a 2D space to a 3D space. 14-dimensional space is very big and very complicated. So we're going to start off by thinking about weight space. This is a space that has one dimension for each weight in the perceptron. A point in the space represents a particular setting of all the weights. Assuming we've eliminated the threshold, we can represent every training case as a hyperplane through the origin in weight space. So points in the space correspond to weight vectors, and training cases correspond to planes. And for a particular training case, the weights must lie on one side of that hyperplane in order to get the answer correct for that training case. So let's look at a picture of it so we can understand what's going on. Here's a picture of weight space. The training case, we're going to think of one training case for now. It defines a plane, which in this 2D picture is just the black line. The plane goes through the origin, and it's perpendicular to the input vector for that training case, which here is shown as a blue vector. We're going to consider a training case in which the correct answer is 1, and for that kind of training case, the weight vector needs to be on the correct side of the hyperplane in order to get the answer right. It needs to be on the same side of the hyperplane as the direction in which the training vector points. For any weight vector, like the green one, that's on that side of the hyperplane, the angle with the input vector will be less than 90 degrees. So the scalar product of the input vector with the weight vector will be positive. And since we already got rid of the threshold, that means the perceptron will give an output of 1. It'll say yes, and so we'll get the right answer. Conversely, if we have a weight vector like the red one that's on the wrong side of the plane, the angle with the input vector will be more than 90 degrees, so the scalar product of the weight vector and the input vector will be negative, and we'll get a scalar product that's less than 0, so the perceptron will say no, or 0, and in this case we'll get the wrong answer. So to summarize, on one side of the plane, all the weight vectors will get the right answer, and on the other side of the plane, all the possible weight vectors will get the wrong answer. Now let's look at a different training case in which the correct answers are 0. So here we have the weight space again. we've chosen a different input vector, and for this input vector, the right answer is 0. So again, the input case corresponds to a plane shown by the black line, and in this case, any weight vectors that make an angle of less than 90 degrees with the input vector will give us a positive scalar product, and so they'll cause the perceptron to say yes or 1, and it will get the answer wrong. Conversely, any input vectors on the other side of the plane will have an angle of greater than 90 degrees, and they will correctly give the answer of 0. So as before, the plane goes through the origin, it's perpendicular to the input vector, and on one side of the plane all the weight vectors are bad, and on the other side they're all good. Now let's put those two training cases together in one picture of weight space. Our picture of weight space is getting a little bit crowded. I've moved the input vectors over so we don't have all the vectors in quite the same place. And now you can see that there's a cone of possible weight vectors, and any weight vectors inside that cone will get the right answer for both training cases. Of course, there doesn't have to be any cone like that. It could be there are no weight vectors that get the right answers for all of the training cases. But if there are any, they'll lie in a cone. So what the learning algorithm needs to do is consider the training cases one at a time and move the weight vector around in such a way that it eventually lies in this cone. One thing to notice is that if you get a good weight vector, that is something that works for all the training cases, it'll lie in the cone. And if you get another one, it'll lie in the cone. And so if you take the average of those two weight vectors, that will also lie in the cone. That means the problem's convex. The average of two solutions is itself a solution. And in general in machine learning, if you can get a convex learning problem, that makes life easy. In this video, we're going to look at a proof that the perceptron learning procedure will eventually get the weights into the cone of feasible solutions. I don't want you to get the wrong idea about the course from this video. In general, it's going to be about engineering, not about proofs of things. There'll be very few proofs in the course. But we get to understand quite a lot more about perceptrons when we try and prove that they will eventually get the right answer. So we're going to use our geometric understanding of what's happening in weight space as a perceptron learns to get a proof that the perceptron will eventually find a weight vector that gets the right answer for all of the training cases if any such vector exists. And our proof is going to assume that there is a vector that gets the right answer for all training cases. We'll call that a feasible vector, and an example of a feasible vector is shown by the green dot in the diagram. So we start with a weight vector that's getting some of the training cases wrong, and in the diagram we've shown a training case that it's getting wrong. And what we want to show, this is the idea for the proof, is that every time it gets a training case wrong, it will update the current weight vector in a way that makes it closer to every feasible weight vector. So we can represent the squared distance of the current weight vector from a feasible weight vector as the sum of a squared distance along the line of the input vector that defines the training case and another squared distance orthogonal to that line. The orthogonal squared distance won't change, and the squared distance along the line of the input vector will get smaller. So our hopeful claim is that every time the perceptron makes a mistake, our current weight vector is going to get closer to all feasible weight vectors. Now this is almost right, but there's an unfortunate problem. If you look at the feasible weight vector in gold, it's just on the right side of the plane that defines one of the training cases. And the current weight vector is just on the wrong side, and the input vector is quite big, so when we add the input vector to the current weight vector, we actually get further away from that gold feasible weight vector. So our hopeful claim doesn't work, but we can fix it up so that it does. So what we're going to do is we're going to define a generously feasible weight vector. That's a weight vector that not only gets every training case right, but it gets it right by at least a certain margin, where the margin is as big as the input vector for that training case. So we take the cone of feasible solutions, and inside that we have another cone of generously feasible solutions, which get everything right by at least the size of the input vector. And now our proof will work. Now we can make the claim that every time the perceptron makes a mistake, the squared distance to all of the generously feasible weight vectors will be decreased by at least the squared length of the input vector, which is the update we make. So given that, we can get an informal sketch of a proof of convergence. I'm not going to try and make this formal. I'm more interested in the engineering than the mathematics. If you're a mathematician, I'm sure you can make it formal yourself. So, every time the perceptron makes a mistake, the current weight vector moves and it decreases its squared distance from every generously feasible weight vector by at least the squared length of the current input vector. And so the squared distance to all the generously feasible weight vectors decreases by at least that squared length. And assuming that none of the input vectors are infinitesimally small, that means that after a finite number of mistakes, the weight vector must lie in the feasible region if this region exists. Notice it doesn't have to lie in the generously feasible region, but it has to at least get into the feasible region to stop it making mistakes. And that's it. That's our informal sketch of a proof that the perceptron convergence procedure works. But notice, it all depends on the assumption that there is a generously feasible weight vector. And if there is no such vector, the whole proof falls apart. In this video, we're going to look at the limitations of perceptrons. These limitations stem from the kinds of features you use. If you use the right features, you can do almost anything. If you use the wrong features, they're extremely limited in what the learning part of a perceptron can do. And that's what caused perceptrons to go out of favour. And it emphasises that the difficult bit of learning is to learn the right features. There is still a lot you can do with learning, even if you don't learn features. For example, if you want to say whether a sentence is a plausible English sentence, you could hand define a huge number of features and then learn how to weight them in order to decide whether a particular sentence is likely a good English sentence. But in the long run, you need to learn features. So the reason that neural network research came to a halt in the late 1960s and early 1970s is that perceptrons were shown to be very limited, and we're now going to understand what those limitations are. If you're allowed to choose the features by hand, and if you use enough features, you can make a perceptron do almost anything. Suppose, for example, we have binary input vectors, and we create a separate feature unit that gets activated by exactly one of those binary input vectors. We'll need exponentially many feature units, but now we can make any possible discrimination on binary input vectors. So for binary input vectors, there's no limitation if you're willing to make enough feature units. But of course, that's not a very good strategy for solving a practical problem, because you need an awful lot of feature units, and it won't generalize. You can't look at a subset of all possible cases and have any hope of getting the remaining cases right, because those remaining cases require new feature units, and you don't know what weights to put on those feature units. Once you've decided the hand-coded features, that is, once they've been determined, there are very strong limitations on what a perceptron can learn to do. So here's a classic example. What we're interested in is, what can you learn to do with the binary threshold decision unit that is by changing its weights. And we're going to show that there's very simple things that it can't learn to do. So the simplest example is, consider a problem in which there's 2 positive cases and 2 negative cases. And the features are just single bit features that have values either 1 or 0. So the 2 positive cases consist of both features being on, in which case the right answer is 1, or both features being off, in which case the right answer is 1. And the 2 negative cases are when one feature is on and the other one's off, in which case the right answer is 0. So all we're asking the binary threshold unit to do is decide whether the 2 features have the same value. And it can't even learn to do that. We can prove that algebraically. Those 4 input-output pairs that I showed you give rise to 4 inequalities, and it's impossible to satisfy them. So the first positive case, when the 2 feature values are 1, the output should be 1. That gives us the inequality that 1 times W1 plus 1 times W2 has got to be greater than the threshold, so we give an output of 1. And the second positive case gives us the inequality that 0 times W1 plus 0 times W2 must also be greater than the threshold. And the negative cases give us the inequalities that 1 times W1 plus 0 times W2 must be less than the threshold, and similarly 0 times W1 plus 1 times W2 must be less than the threshold. Now if you take those first 2 inequalities and you add them up, you get that W1 plus W2 must be greater than twice the threshold. And if you take the second 2 inequalities and you add them up, you get W1 plus W2 must be less than twice the threshold. So there's clearly no way to satisfy all 4 inequalities. Or to put it another way, if you look at the binary decision unit, where we're going to put the threshold as a negative weight on an input line that always has value of 1, if you take that binary threshold unit shown at the bottom right, there's no way to set the threshold and the 2 weights, so it gets all 4 cases right. We can also see this geometrically. So we're going to imagine a data space now in which the axes correspond to components of an input vector. So in this space, each point corresponds to a data point, and a weight vector is going to define a plane in this space. So it's just the opposite of what we're doing with weight space. In weight space, we made each point be a weight vector, and we used a plane to define an input case. Of course, that plane was defined by an input vector. Now what we're going to do is we're going to make each point be an input vector, and we're going to use a weight vector to define a plane in the data space. The plane defined by the weight vector is going to be perpendicular to the weight vector, and it's going to miss the origin by a distance equal to the threshold. So here's a picture. You see the 4 data cases there, and for the 2 data cases in red, we need to give an output of 0, and with the 2 data cases in green, we need to give an output of 1. That means we need the green cases to be on the side of the weight plane where the output is 1, and we need the red cases to be on the side where the output is 0, and we obviously cannot arrange the weight plane so that that's true. We call a set of cases like that where there's no hyperplane that will separate the cases where we want the answer to be 1 from the cases where we want the answer to be 0. We call that a set of training cases that's not linearly separable. An even more devastating example for perceptrons, because it's much more general, is when we try and discriminate simple patterns that have to retain their identity when you translate them with wraparound. I'll give you an example of what that means in a minute. But the idea is that we want to recognize a pattern, and we want to recognize it even when it's translated. So suppose we just use pixels as the features. The question is, can a binary threshold unit discriminate between two different patterns and call one positive example and the others negative examples if they've got the same number of pixels in them? And the answer is no, it can't discriminate two patterns that have the same number of pixels if that discrimination has to work when the patterns are translated and if the patterns can wrap around when they translate. So if you look at these examples of pattern A in a one-dimensional image, pattern A has 4 pixels that are on, those 4 black pixels. It's like a little barcode. And it's the same pattern when we translate it a bit to the right. And we're going to allow ourselves to translate the pattern so it goes off the right-hand end and comes back on the left-hand end. So the third example is the same pattern that's been translated with some wraparound. And pattern B, it also has 4 patterns, but 4 pixels, but in a different arrangement. And in the third example of pattern B, it's been translated with wraparound. So that's still an example of pattern B. And for 2 sets of patterns like that, a binary threshold unit cannot learn to discriminate them. And here's a proof. What we're going to do is we're going to consider that for the positive examples, we have pattern A in all possible translations. Now, since pattern A has 4 on pixels, that means if we look at any pixel on the retina, there'll be 4 different positions in which we can put pattern A that will activate that pixel. So each pixel will be activated by 4 different translations of pattern A. That means that the total input received by the decision unit over all those various translations of pattern A will be 4 times the sum of all the weights in the perceptron, because each pixel will activate the decision unit 4 different times. And so summed over all those patterns, we'll get 4 times the sum of the weights. Now consider pattern B. We're going to make the negative cases be pattern B in all possible translations. And again, each pixel will be activated by 4 different translations of pattern B. So the total input that the decision unit receives over all those different translations of pattern B will again be 4 times the sum of all the weights. But the perceptron, in order to discriminate correctly, has to have weights so that every single case of pattern A provides more input to the decision unit than every single case of pattern B. And that's clearly impossible if, when you sum over all these cases, all those different versions of pattern A and all those different versions of pattern B provide exactly the same amount of input to the decision unit. So we've proved that a perceptron cannot recognize patterns under translation if we allow wraparound. That's a particular case of Minsky and Pappert's group invariance theorem. And that result is devastating for perceptrons. It was historically devastating. Because the whole point of pattern recognition is to recognize patterns that undergo transformations and see that they're still the same pattern despite the transformation. Like, for example, translation. And when Minsky and Papert showed that a perceptron couldn't do that if the transformations formed a group, that is, the learning part of a perceptron couldn't learn to do that, it became clear that the claims that had been made for what perceptrons could learn were somewhat exaggerated, and that to get them to do anything interesting, you had to choose just the right features to make it fairly easy for the last stage to learn the classification. So the translations with wraparound form a group, and Minsky and Papert proved a general theorem that transformations that form a group make it impossible for a perceptron, for the learning part of a perceptron, to do the recognition. The perceptron architecture can still do the recognition, but you have to organize the features so they do the difficult part. So we have to have multiple feature units that recognize informative subpatterns that tell you something about what class it is, and we have to have separate feature units for each position of those informative subpatterns. if we're trying to recognize under translation. So the tricky part of pattern recognition has to be solved by the hand-coded feature detectors, not the learning procedure. The temporary conclusion from this is that perceptrons are no good and therefore neural networks are no good. The longer-term conclusion is that neural networks are only going to be really powerful if we can learn the feature detectors. It's not enough just to learn weights on feature detectors, we have to learn the feature detectors themselves. And the second generation of neural networks, which we'll come to in the next lecture, was all about how you learn the feature detectors. But it took 20 years before people figured out how to do that. So networks without hidden units are very limited in what they can learn to model. If we have more layers of linear units, it doesn't help because everything's linear. We can make them much more powerful by putting in hand-coded hidden units, but they're not really hidden units because we hand-coded them. We told them what to do. It's not enough just to have fixed output nonlinearities. What we need is multiple layers of adaptive, nonlinear hidden units. And the problem is, how can we train such nets? We need a way to adapt all the weights, not just the last layer like in a perceptron. And that's hard. In particular, learning the weights going into the hidden units, that's equivalent to learning features. And that's a hard thing to do because nobody's telling us directly what the hidden units should be doing, when they should be active and when they should not be active. And the real problem is, how do we figure out how to learn those weights going into hidden units so that the hidden units turn into the kinds of feature detectors we need for solving a problem when nobody is telling us what the feature detectors should be?